we're going to consider the special case of a first-order nonlinear DE. This is something that's called a separable DE. Now remember, whenever we solve a first-order problem, there's an independent variable, the input, and then there's a dependent variable, the output, the function. In a separable DE, what's happening is that the right-hand side is separated into one function that depends explicitly on the independent variable, the input, and another function that depends explicitly on the output, h of y. We're going to go ahead and take a look at this. Because of this special structure, it allows us to do some stuff, do some algebra. Assuming that h of y isn't 0, we're going to divide through by this h of y. We're going to group together everything with a y on one side and leave the other term alone. Of course, when h of y is 0, we should expect something bad to happen with the solution if it exists at all. We'll do a rename here. We'll call this thing n of y. And what we've got now is n of y, y prime of t equals g of t. We've somehow separated the y dependence from the t dependence. Now, just as some notation, let's let capital N of y be the antiderivative of n of y. Why do we care about this? Because if you take a look at the left-hand side, the left-hand side ends up being a perfect derivative of a composite function by the chain rule. So this ends up being the derivative of this thing, and capital N of y of t, and that equals g of t. So this allows us to antidifferentiate both sides, and let's say that g of t is the antiderivative of little g. So if we give this notation there, then what ends up happening is we've got the following result. N of y equals g of t plus c. So symbolically, this is something new. When we've got an explicit solution, like we have seen, that means we would get y of t equals some function. And this would solve the DE. It makes the right-hand side equal the left-hand side for the DE. Now, we don't have that here. We've got something called an implicit solution. An implicit solution is a little different. An implicit solution means that I can reorganize this entire equation, put all the variables on one side, and it's going to equal some constant on the other. Now, you should see here in our case, we've got n of y minus g of t. This is my side, and it equals a constant. If we take a look at the derivative, if we differentiate, we will still see that this equation will make the left-hand side equal the right-hand side in the DE. So this thing is what we're after. So how do we get this implicit solution? How to get the implicit solution from a DE? And this is something very easy that you've done in calculus. If you're given this DE, and again, it's separable, just like I outlined earlier, you're going to divide through by both sides. You're going to divide through by this h of y. And then what's going to happen is you're going to take an antiderivative of both sides. Now, it is not a different antiderivative. In order to preserve equality, you must take the same antiderivative on both sides. From calculus, you learn that this could be redefined as a new differential dy. It just essentially the chain rule in reverse. You're switching variables here. It's a change of variables, and what ends up happening is that you're going to get two different antiderivatives on either side. Remember that we called this n of y dy, And this is a very mechanical way for us to get the solution that we're after. We'll end up getting this n of y equals g of t plus a constant. The constant is very important. And if we don't include that constant, what's going to happen is that we are going to forget an important term. So here's a specific example here. Here's a special example that we're going to take a look at to try to illustrate this method. So we've got a first order equation. dy dx is given by this. It's an initial value problem. And note, straight away, in this case, we are lucky. Most nonlinear equations, it's difficult to determine if bad things will happen. Well, in this particular case, we can see that if y squared minus 3 is equal to 0, or y equals plus or minus root 3, we're going to see that the slope will be undefined. So we should expect that when we solve this, somehow we will see that behavior. We should also note that this is separable. dy dx is 2 minus x times 1 over y squared minus 3. All the x dependence is separated as a product from all the y dependence. So we're ready to go. We can find this and determine what we need. So we're going to move the term with the y squared. Everything with the y goes together with the derivative. So we'll have a y squared minus 3, y prime of x on one side is 2 minus x on the other side. We're going to anti-differentiate both sides with respect to x. That's how we preserve equality. And what this means is this term will end up giving us a dy. It's effectively the chain rule in reverse. It's a switch of variables. When we do this, what we're going to end up with is a solution. Y cubed over 3 minus 3y is 2x minus x squared over 2 plus a constant. The constant needs to be there. This is going to end up being our implicit solution. We're going to group together all the terms with x and y. We'll have y cubed over 3 plus x squared over 2 minus 2x minus 3y equals this constant. And so, what do we do with this, right? There's our function of x and y. We can't unjumble this. We cannot isolate y. So we're not going to get an explicit solution, y of x. That's a fact of life with nonlinear differential equations. Sometimes you're going to be able to isolate for y, sometimes you won't. The other thing that's even worse about this and with nonlinear differential equations is, what does this do? This is great. I got a solution. What does the solution do? Right? Big deal. Unfortunately, with nonlinear equations, it's possible to get formulas, but they don't really help you. What we need to do is we need to visualize this with Maple or some other software. What we can do is plot the slope field or the direction field for the entire differential equation. What we can also do is plot this f of x and y equals a constant for different c values. And as an example of that, I've plotted the solution to this differential equation. So this looks like a bit of a mess, and I'm going to try to walk you through what's happening here. Now, in this particular case, we've got several things going on. You can see the slope field. That's great. These equations, f of x, y equals c, these are called level curves of the function f. And that's what you're seeing here as trajectories. These are represented as trajectories in this picture. Now, the initial condition here was given y of 1 equals 1. If you were to plug this into the solution that we got, x squared over 2 plus y cubed over 3 minus 3y minus 2x equals a constant, if you take and you sub this in, you'll find that c is negative 25, I believe it is. So if you plug that in, you'll get c is negative 25. If you want to look at this visually, on this graph, the point 1, 1 is right there. Now, there's some other stuff going on that we determined from the function. Remember that when y was equal to root 3, and when y was equal to negative root 3, we had some problems with the derivative and the slope. So this is y equals root 3. And then down here is the other spot where y equals negative root 3. You can see that at every point on every one of these trajectories, we have a vertical tangent line. So that was to be expected. We got lucky in this non-linear differential equation. Generally, when we have an implicit solution like this, this is not a function. So it's not going to pass the vertical line test. So when you've got this initial condition, if we were to plot the level curve for this thing equal to negative 25, it turns out that there are 3 portions, and they're all in this darkened line. So this portion corresponds to that level curve, and then these 2 as well. So you've got 1, 2. They form this ellipse type result. This is the only portion that satisfies the initial conditions. So the level curve gives us 3 separate functions in 3 different regions, but that's the only one that will satisfy the initial conditions and the differential equation. So if you want to visualize this, Maple's command of implicit plot will help you do the job. I'm hoping that you can see out of this that, number one, the formula isn't really useful. Sure, we can do some algebra and calculus and get a formula with x's and y's, but unless I have Maple to visualize this, it's pretty difficult to get any understanding of what's going on. Once you get a picture of what's going on, you can see, okay, the slope field is doing this, the solution trajectories are going to live in 3 separate regions, bounded by those lines, and in each one of those regions I will have some sort of trajectory determined by that level curve. So what's much more important is the behavior rather than the solution. Now you can get a lot of mileage out of this separable technique, and we are going to try to exploit this as best we can as it relates to linear systems.